Section 8.3, Molecular Structures. The objectives of this lesson is to list the basic steps used to draw Lewis structures, explain why resonance occurs, and identify resonance structures, identify 3 exceptions to the octet rule, and name molecules in which these exceptions occur. Some vocabulary review will be ionic bond, and some new vocabulary you'll come across are structural formulas, resonance, and coordinate covalent bond. In Chapter 7, you learned about the structure of ionic compounds, substances formed from ionic bonds. The covalent molecules you have read about in this chapter have structures that are different from those of ionic compounds. In studying the molecular structures of covalent compounds, models are used as representations of the molecule. The molecular formula, which shows the element symbols and the numerical subscripts, tells you the type and number of each atom in a molecule. If we look at figure 8.13, there are several different models that can be used to represent a molecule. Note that in the ball and stick and space-filled molecular models, atoms of each specific element are represented by spheres of a representative color. These colors are used for identifying the atoms if the chemical symbol of the element is not present. One of the most useful molecular models is the structural formula, which uses letter symbols and bonds to show relative positions of atoms. You can predict the structural formula for many molecules by drawing Lewis structures. You have already seen some simple examples of Lewis structures, but more involved structures are needed to help you determine the shapes of molecules. So if we look at this figure here, the molecular formula gives us good information. It tells you what atoms and how many of each atom may exist. And the structural formula tells us how they're sort of arranged. But I find that the Lewis structure is probably the most helpful because it tells us how they're bonded as well as our lone pair of electrons. And that's going to be helpful when we get into higher levels of chemistry. And again, when you get into higher levels of chemistry, you kind of get this eye for the different colors and the different atoms. And we can use the ball and stick as well as the space-filling model to kind of give us what they would actually sort of look like in terms of relative size of the elements. Right, the P and the H, they're kind of the same size. However, if we kind of know, go back to the atomic radii of some of these molecules, right, some of these atoms get larger, and that's what's great about the space filling in the ball and stick, that they give relative size as we go along. Although it's fairly easy to draw Lewis structures, for most compounds formed by nonmetals, it's a good idea to follow a regular procedure. Whenever you need to draw a Lewis structure, let's follow these steps outlined below. I'm not going to go into great detail in each step, but I'm just going to kind of give it a brief idea. All right, so the first thing you're going to want to do is you want to go ahead and predict the location of certain atoms. Usually how I look at this is that your nonmetals that are farther to the left of that little nonmetal group will be your central atoms, and these are the atoms that can do more bonding, right? Carbon has the potential of doing more bonding because it has 4 free valence electrons. Hydrogen will always be a terminal atom. It'll always be on the end because it only has that potential of 1 valence electron bonding, and it can't expand its octet that we'll learn about in a little bit. Hydrogen cannot expand its octet, so hydrogen will always be on the end. Then you're going to want to go ahead and determine the number of electrons that are available for bonding, and then determine the number of bonding pairs that occur within that molecule. Then you're going to want to go ahead and place the bonding pairs between your central atom and your terminal atoms, and then find out how many of these bonds all remain in the end after you've done your bonding pairs. And these are going to go ahead and Once you determine how many bonds remain, you probably have to go back and look at this and ask yourself, does this satisfy the octet rule? Do you have to do lone pair electrons on some of these terminal atoms or the central atom, or do you have to go ahead and do double and triple covalent bonds to make this happen? Step 6 is determine whether the central atom then satisfies the octet rule. Right? And the name of the game, right, is always to have that octet rule. That's why these atoms are sharing these electrons so that they can go ahead and be satisfied as a noble gas. I think the best way to go ahead and explain these, to better understand them, is just to do an example. All right. Ammonia is a raw material used in the manufacture of many materials, which include fertilizers, cleaning products, and explosives. Let's go ahead and draw the Lewis structure for ammonia. And ammonia is a common name for NH3. So we know that ammonia consists of one nitrogen atom and 3 hydrogen atoms. We know that hydrogen is going to be our terminal atom, so therefore it kind of puts nitrogen in the center here. But let's go ahead and find out how many valence electrons actually exist in this atom, this molecule, so that we can go ahead and figure out where are we putting all of these electrons. For every one nitrogen atom, we know that it has 5 valence electrons. And we know that is if we go back to our periodic table, right, we can see that nitrogen is a group 15 element, and they all have 5 valence electrons. And here we go, we look at hydrogen. Hydrogen is a group 1 element. And again, even though it's on the metal side, you have to kind of think about hydrogen being a non-metal. So, nitrogen has 5, hydrogen has 1. Right, let's find out how many total electrons that we have. Right, do your arithmetic, you add them all up, you have 8 valence electrons. So we know that there are 2 electrons for every pair. So we're going to go ahead and divide those 8 electrons by 2 electrons that exist for every pair. And we know that 4 pairs exist in this molecule itself. So we're going to go ahead and take that nitrogen and surround it with the 3 hydrogens, and we're going to go ahead and draw lines in between each of those. And this goes and will represent the bonds between the nitrogen and the hydrogen, with the hydrogens as your terminal atoms. Now if we kind of add all of these up, right, we just used 3 pairs of electrons when we had a total of 4, which means that we have 1 pair that's left over. If you look at this, we can say, right, that nitrogen, let's start with hydrogen, right? Hydrogen now has, right, 1 bond, which means 2 electrons, and now hydrogen's octet is satisfied. And each of these hydrogens' octets are satisfied. However, nitrogen really only has 2, 4, 6 electrons surrounding it, right? Its octet is not satisfied, so it must need 2 electrons. And as we noted before, that there is 1 pair that is still available, so that must be the lone pair of electrons that we find on nitrogen. So this is what our molecule of ammonia would look like when we're drawing the Lewis structure. And I said I like the Lewis structures a lot more because it gives us more information, especially when we got to go ahead and find the geometry of these molecules. All right, so let's go ahead and I'll let you guys take a little practice on this. Draw the Lewis structure for BH3, boron trihydride. And if you want to pause the video, right, and give this a try. Right, so this is the answer for boron trihydride. Right, and your molecule looks a little something like this. Right, notice how this does not have any lone pairs, and we'll talk a little later how boron trihydride actually is an exception to this rule. All right, So sometimes you get covalent compounds with multiple covalent bonds, right? Doubles or triples. Carbon dioxide is an example of that. Right? Carbon dioxide is a product of cellular respiration. All right, so let's draw the structure for carbon dioxide. All right, we know that carbon is on the left side of that non-metal group, because it has the potential of 4 valence electrons. Right, chances are that it is going to be our central atom. But let's go ahead and count up all of the potential electrons available for this molecule. We have 1 carbon atom, and each carbon atom has 4 electrons, and we have 2 oxygen atoms, and each of those have a potential of 6 valence electrons for a total of 6 valence electrons in this said molecule. Right, take that 16, divide it by 2, and that's telling us we have 8 pairs that could exist in this molecule. So let's go ahead and draw carbon as our central atom with our oxygens on the ends, our terminal atoms. And when we go ahead and draw in those lines, right, it tells us that we've just used 2 pairs of electrons. Right, take that 8 divided by the 2 that we used, we have 6 pairs that are left over. Right? So now what we're going to want to go ahead and do is we're going to want to go ahead and put lone pairs on the terminal oxygen atoms. Right? So when we do that, we get, right, let's just look at this oxygen here. Right? If we look at this oxygen, it has 2, 4, 6, 8. Right? That line is also 2 electrons that are being shared. So this oxygen octet is satisfied. Right? Look at this one, 2, 4, 6, 8. This oxygen's octet is satisfied, but if we go ahead and look at carbon, this octet is not satisfied. So even though we have 0 pairs left over, we have to also say to ourselves, well, yeah, the oxygen is satisfied, right? But there's no satisfaction to the carbon. So what actually happens is that this oxygen is going to want to go ahead and share these 2 electrons on the top with the carbon atom, and this oxygen is going to share its 2 electrons with the carbon, right? And when doing so, right, we'll get these double covalent bonds forming. Now if we look at this, even though this oxygen shared its lone pairs of electrons with carbon, its octet is still satisfied. 2, 4, right, 6, and 8 valence electrons for this oxygen, even though 4 of them are being shared with the carbon. And the same thing goes with this oxygen. 2, 4, right, and the 6 and the 8 are also being shared with that carbon. But if we look at the carbon, remember that each line represents 2 valence electrons, right? Carbon has 2, 4, 6, 8 electrons, and now its octet is satisfied. So let's draw the Lewis structure for ethylene, C2H4. So you want to pause the video and give this one a try. All right. So here is the answer for ethylene. Right, this is our preliminary molecule, right? Even though our hydrogen's octets are satisfied, right, this carbon only has 2, 4, 6. This carbon only has 2, 4, 6, right? But we have that 1 pair that's left over. So to go ahead and complete the octet, we have to go ahead and create a double bond between the 2 carbons, right? And this carbon now has 2, 4, 6, 8, right? Its octet is satisfied. And this carbon, right, has 2, 4, 6, 8. Its octet is satisfied. Although they act as a unit, as an ion, the atoms within a polyatomic ion are covalently bound. So, right, it's a molecule that acts as an ion. I know it's a little kind of abstract, but these things do happen in nature. The procedure for drawing Lewis structures for polyatomics is similar to that of drawing for covalent compounds. The main difference is in finding the total number of electrons for bonding. Compared to the number of valence electrons present in the atoms that make up the ion, more electrons are present if the ion is negatively charged, and fewer are present if the ion is positively charged. To find the total number of electrons available for bonding, first find the number available in the atoms present in the ion. Then subtract the ion charge if the ion is positive, and then or add the ion charge if it is negative. So let's go ahead and draw the Lewis structure for phosphate, PO4 3. All right, we know it consists of a phosphorus. It also contains 4 oxygens, but the additional information here is that it has a -3 charge. So it has 3 additional electrons that must be added into this. So again, the same thing that we were doing for the Lewis structure of covalent compounds. The only thing different here is that we're going to go ahead and add 3 electrons because it is a negative charge. So we have a total of 32 electrons that are available in this compound. Take that 32 and realize that we have 16 pairs that we need to go ahead and make. So let's just go ahead, right? Phosphorus is farther to the left on the periodic table in the nonmetal section, so it's probably going to be our central atom. All right, we're going to make oxygen as our terminal atoms, right? And in doing so, we've used 4 pairs, so that means we have 12 pairs available for this molecule. So what we want to go ahead and do is put our lone pairs on the central atoms first, right? And in doing so, we're going to go ahead and add, right? We have 12 pairs available. If we put 1, 2, 3 pairs on each oxygen, for oxygen, right, it uses those 12 pairs. So when making this molecule, what's going on here? When making this molecule, right, it's also pretty good when you have this Lewis structure to go ahead and put parentheses around the whole thing. And just note that it has a -3 charge, right? This would be the more proper way of doing it. All right, let's go ahead and try and create perchlorate ion. Right, perchlorate's an interesting one. This one kind of doesn't follow that rule. Chlorine can expand its octet, and again, that's something we'll talk about later. Hint, chlorine will be your central atom. So go ahead and pause the video and give this one a try. All right. So this is what it would look like for perchlorate. All right, same thing that we've done before. 16 pairs are available. Right, I went ahead and I put my chlorine as my central atom, created my bonds with the oxygens. 12 were left over. Right, and then I just put on my lone pairs of electrons on the outside. Right, those 12 pairs will be used as my lone pairs, and again I just put it all in brackets with a -1 charge. All right, resonance. Let's get that picture up there. Using the same sequence of atoms, it is possible to have more than one correct Lewis structure when a molecule or polyatomic ion has both a double bond and a single bond. Consider the polyatomic ion, where we at nitrate, which is NO3 1-, as we look in 814. right, we can have 3 equivalent structures for one given ion. When we go ahead and do the Lewis structure for a polyatomic that we just did in the last example, right, you can go ahead and get this compound with the double bond on this oxygen, but that's not to say that you can't have the double bond on this oxygen, and that's not to say that you can't have the double bond on this oxygen, right? You can have them on 3 different oxygens, and all of them are valid. And in chemistry, what will happen is that double bond just tends to kind of shift around. And what it does is, as it's shifting around, that double bond could be anywhere and everywhere. So what we do in chemistry is we use these dotted lines to indicate that this double bond could be here, could be there, could be here, could be anywhere amongst those 3 possible locations in this given molecule. And if you guys take chemistry in college, you'll learn that resonance actually equates to stability. Right, so this is why one of these things can actually happen. Resonance is a condition that can occur when more than one valid Lewis structure can be written for a molecule. The 2 or more correct Lewis structures that represent a single molecule or ion are referred to as resonance structures. Resonance structures differ only in the position of the electron pair, never the atom positions. The location of the lone pair and the bonding pair differs in resonance structures. The molecules O3, or ozone, and the polyatomics of nitrate, nitrite, sulfate, and carbonate commonly form resonance structures. It is important to note that each molecule or ion that undergoes resonance behaves as if only one structure. Right? So like I said, that these double bonds are always constantly shifting. So if you kind of like think about it as the propellers of an airplane, right, you kind of get this blurring effect, so to speak, and then this double bond could be anywhere at any given time. So really it behaves as if it's only one structure. And that's kind of why we use them dotted lines, as you saw in 814b, right? Because those double bonds could be anywhere at any given time. Experimentally measured bond lengths show that the bonds are identical to each other. So again, it's almost like it takes over the whole. The bond is not either double or single; it's a resonance bond that exists. So the actual bond length is an average in the resonance structures. All right, so let's go ahead. I'll give you guys a practice problem. All right, give that a try. Use what you learned from the previous problem and try and go ahead and create the resonance structures for that of nitrate. Excuse me, nitrite. So go ahead and pause the video and give this one a try. All right. So here's nitrite. So if we look at this, right, this is our preliminary molecule, right? Oxygen's octet satisfied, oxygen's octet is satisfied. However, nitrogen's octet is not satisfied. So what we can do is that we have that one pair left over. That double, excuse me. This oxygen could donate its double bond, or this oxygen can donate and form a double bond, right? So you can get either one of these to occur, right? But more traditionally, we would go ahead and say is that the resonance structure can exist, right? And this is kind of what we're looking at. So again, all of these structures are pretty valid, right? To note this, you must note this, right? But really, this is kind of what we're observing in real time. So generally, atoms attain an octet when they bond with other atoms. Some molecules and ions, however, do not obey the octet rule. There are several reasons for this exception. Odd number of valence electrons, for example. First, a small group of molecules might have an odd number of valence electrons and might be unable to form an octet around each atom. For example, NO2 has 5 valence electrons from nitrogen and 12 from oxygen, totaling 17, which cannot form an exact number of electron pairs. Right? So if we look at this figure here, right, this nitrogen has an incomplete octet. ClO2, NO are other examples of molecules with odd number of valence electrons. Another exception to the octet rule is due to a few compounds that form suboctets, stable configurations with fewer than 8 electrons present around an atom. This group is relatively rare, and BH3 is an example. Boron, a group 3 nonmetal, forms 3 covalent bonds with other nonmetallic atoms. The boron atom shares only 6 electrons, too few to form an octet. Such compounds tend to be reactive and can share an entire pair of electrons donated by another atom. And we call this a coordinate covalent bond. These form when one atom donates both of the electrons to be shared with an atom or an ion that needs 2 electrons to form a stable arrangement with a lower potential energy. So if we look at 816, I think that's a good example, right? Here we have ammonia, right, NH3 and BH3, and what can happen is that a coordinate covalent bond forms when nitrogen's lone pair of electrons shared with boron, right? And now boron here, right, has a complete octet, right? Even nitrogen now has a complete octet because, again, it's still 2, 4, 6, 8. But now in this case, boron also has a complete octet because, again, it's 2, 4, 6, 8 electrons in there. And this happens all the time in chemistry. Coordinate covalent bonds are nothing rare. Atoms or ions with lone pairs often form coordinate covalent bonds with atoms or ions that need those 2 extra electrons. The third group of compounds that do not follow the octet rule has central atoms that contain more than 8 valence electrons. This electron arrangement is referred to as an expanded octet. An expanded octet can be explained by considering the d orbital that occurs in the energy levels of elements in periods 3 or higher. And again, here's those funny d orbitals, right? They're coming in, and because if you have an energy level of 3 or higher, you're close to that d orbital, and again, it can expand its octet. An example of an expanded octet, right, we'll see in 817 is the bond formation of PCl5. 5 bonds are formed with 10 electrons shared in one s orbital, 3 p orbitals, and 1 d orbital. Another example is the molecule sulfur hexafluoride, which has 6 bonds sharing 12 electrons in an s orbital and 3 p orbitals and 2 d orbitals. When you draw the Lewis structures for these compounds, lone pairs are added to the central atom, or more than 4 bonding atoms are present in the molecule. Right, so here's just kind of an example. Right, you can have phosphorus trichloride reacting with diatomic chlorine, and when it does, it expands the octet of the phosphorus, creating phosphorus pentachloride. Let's look at this example. Xenon is a noble gas that will form a few compounds with nonmetals that strongly attract electrons. Let's draw the correct Lewis structure for xenon tetrachloride. Right, so we're going to do the same thing that we've been doing all this time. Let's find out how many valence electrons are available in this given compound. Now, I know probably some of you are looking at this and you're saying, well, isn't xenon a noble gas? Well, xenon is one of those noble gases that under the right conditions could actually do some bonding. Under temperature and pressure, again, right conditions, it will expand its octet, and in doing so, form a couple bonds. All right, so xenon is going to be our central atom here. Fluorine are going to be our terminal atoms. So we've used 4 pairs of electrons to go ahead and bond xenon to fluorines, and now we have 14 left over. So let's go ahead and put those 14 pairs to work. We're going to go ahead and use them on the terminal atoms first. So we use, we have 14, that's 1, 2, 3. So we use 12 pairs of electrons. We have 2 unused pairs. Now, fluorine does not expand its octet, so it's just going to stay as is. And these 2 unused pairs are going to go right onto the xenon. And this is what the Lewis structure of xenon tetrachloride would look like. Okay. So let's go ahead and do an example. I'll let you guys try. Chlorine trifluoride. Okay, so pause the video and give this one a try. Because chlorine, is in, what is that? Chlorine is a group, it's a group 17 element, but it's also in period 3, which means that it can go ahead and expand into its d orbitals. Chlorine is going to be our central atom. So let's find out how many pairs we need to go ahead and have. In this case, it's 14 pairs. 14 pairs, we're going to put the chlorine in the center. We have 11 pairs available, so we're going to go ahead and put the lone pairs on our terminal atom first, which means that when we go ahead and do that, we have 2 lone pairs available still. So now we're going to go ahead and put those 2 lone pairs on the carbon atom, chlorine atom, and we get a Lewis structure looking like this. Section summary. Different models can be used to represent molecules. Resonance occurs when more than one valid Lewis structure exists for the same molecule. Exceptions to the octet rule occur in some molecules.